This video is on stereoisomerism, specifically Cis Trans or EZ isomerism. Okay, let's rewind a little bit and go back to your IG level. In IG level, we've learned structural isomers. So if we have something like this, 1,1-dichloroethene, we know clearly that they're not the same as 1,2-dichloroethene. The names are different. They've got the same molecular formula, but different structural formula. So it's clear that they are different. Okay, but now that we've learned about shapes in IB level, we know that if this has 3 bonded pairs of electrons, remember double bond, we treat them as 1 bond pair. So 3 bond pairs, that makes it trigonal planar. So these are 120 degrees, which means an ethene is flat, like that. Okay, what if I draw another one this way? It is still going to be 1,2-dichloroethene in an IG student's point of view. But now at IB level, they're not the same anymore because these are not each other. Although they've got the same names, but their position of the chloros are not the same. One of them is on the same side of this double bond, and the other one is on the opposite side of the double bond, and they can't interchange. Like this chloro cannot just spontaneously change and go to the position of this H. So they're not each other. So a little bit deeper, we have to name them a little bit more in detail. So we don't just name them 1,2-dichloroethene because then we cannot differentiate these two. So how do we name them? We look at whether they are on the same side or they're on the opposite side. That's how we name them now. That's how we differentiate the cis and the trans. So we'll go to cis trans first, then to EZ. Okay, cis trans or E and Z isomer can only arise because of this double bond here. You can't rotate this double bond. What do I mean by I cannot rotate this double bond? I mentioned it earlier. I can't change the position of these chloro and the H here. So I can't just rotate it and change its place. Because if it's able to rotate, then these two would be the exact same thing. But since there's a double bond there, the Cl and the H cannot exchange place. So that's what we meant by not able to rotate that double bond. Okay, so that's the first criteria. It's because rotation about a double bond is restricted. Okay, the second thing you have to look for is this and this. So look at one side of the double bond. The one at the top and the bottom must be different things. Okay, so check on this side and then check on the other side. It also must be different things, any different thing. So let me just put a C here instead. So it just have to be different. So you have to check on the left side, different, and check on the right side, different. Okay, what happens if you check on the left side? It's different. You check on the right side, they're the same. So this will not give you a cis trans or EZ isomerism. Let's discuss the cis trans first. Let's look at a but1 in and a but2 in. Okay, let's look at this criteria first. For a but1 in, on the left side, the carbon is attached to a H and another H. So if it's the same thing, then it will not show cis trans. Although the other side passed test, it's connected to a H and a CH2, CH3. So although this side passed the test, this side did not, because there's two H, same thing. So but1 in will not show this cis trans isomerism. What about but2 in? Okay, so the carbon with the double bond is attached to a H and a CH3. Okay, that's different. And on the right side, it's attached to a H and a CH3. Oh, that's different as well. So this side passed and this as well. Okay, let's draw the cis and trans. Cis is when it's on the same side and trans is when it's on the opposite side. So let's draw it, always draw it in this shape. We now know that these are trigonal planar in shape, so please always draw them in trigonal planar shape. So let's not draw it like this. Let's not draw it this way. Let's make a good habit. Okay, let's settle the left side first. A H and a CH3. So a H and a CH3. On the right side, it's also a H and a CH3, and cis, they have to be on the same side. So I'm going to put a H on the same side, and the CH3 on the same side, same side. So this is a cis butene. Let's draw the trans butene. Okay, I'd like you to take note that you see that this carbon, if you draw a display structure, you'll see that this carbon is bonded to this carbon and not the H. If we were to draw that out, it looks something like this: a H, a C, H2, and a C, a CH3 this way. Okay, so it's a C to a CH3 here. Do you see that the carbon is connected to the carbon here and the carbon is connected to the carbon here, which means I'd like you to be a little bit specific and connect this to the carbon and not the H. Okay, back to the cis trans. So the cis, we had it on the same side. For the trans, just turn it around. The CH3 should be on the opposite side, and the H is opposite. So it's opposite this way, opposite this way. That is a trans butene. If you haven't noticed, it says here that cis and trans will arise when the rotation about a bond is restricted. So it did not say that it must have a double bond as long as the rotation about a bond is restricted. So another option would be having a cyclic compound. So if we have a cyclic compound, for example, this is cyclobutane. This is also possible to show a cis trans if we have different items, different things attached up and down, different things attached up and down. Again, we can't rotate this and exchange their position. That is why they are cis and trans, they're two different structures. Okay, I'll draw one of those. Okay, to simplify the view, I'm going to put it flat like this. The wedge here means that it's coming out of the page, and the dot dot means that this dot 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 means that it's going into the page. And so all the dots are all going into the page and all the wedge are coming out to us. Okay, I'm going to put the chloro here. The rest of it, I'm just going to fill them in with H. And since both the chloros are coming out at us, this is a cis. So that's a cis 1,2-dichlorocyclobutane. Let's draw the trans. The trans, the chloro one will have to come out and the other one will have to go into the page. So I'm going to draw something that looks similar to the cis. Coming out, and going in, going in, and in. Okay, the H, no changes. On the left side, I'm just going to copy the first one. And on the right side, I'm going to turn that around. Therefore, the chloro one is coming out of the page and the other one is going into the page. It's the opposite side, therefore it's a trans. Now let's come back to the first example, this butene. We've already determined how to differentiate the cis and the trans. Now let's look at how do we determine E and Z, which is E and which is Z. Now to do that, you need to know how to determine the priority. Let's go to another slide here. Okay, to know the priority, you will need your periodic table. So for example, if I have a H here, compared to if I have a CH3, what we've got to do to know the priority is get the atomic number. H is 1. And this is connected to C. C is 6. So this is at higher priority. Okay, something a little bit more complicated. What if I have a CH2CH3? Okay, now I want to compare this two, which is at higher priority. So 6, and then I have a 1, 1, 1. And this 6, I have 1, 1, and the further I walk here, it's a 6, whereas this one is a 1. So this is a higher number. This is at a higher priority. What if I have a Cl? A Cl, if I were to compare with this is 6, and this is 6. A Cl is 17. So Cl is at higher priority. Now let's compare these two, which has a higher priority. So I walk this way, I found a 6, same here. And the next would be 1, 1, 6, same here, 6, 1, but I have an O here, it's different. O is 8. So this is at higher priority because the difference is this is 1. Okay, let's compare these two. How do I find out the priority? So walk with me. The first one, 6, same here, 6. And this one, 1. This, same, 1. And now this is the difference. Now if I walk this way, I'll get an 8. And it's a double bond, so another 8. So I look at each of the bonds separately. So an 8 and another 8. What about this one? I get an 8 and a 1. So this is a higher number. This is my priority. So going back to our first and second example, these were very simple examples. So it's clearly that these are 1 and 1, and this is 6 and 6. So same side. The higher priority is on the same side. That would give us a Z. Higher priority at the opposite side, this gives us an E. Okay. Our second example with the cyclo here, the one with a higher priority, it's on the same side, so this is a Z, and opposite side, this is an E. Okay, so it's not difficult at this point, but if we've got 3 different groups, then it might be different this time. Earlier on, it looks as if cis is always Z and trans is always E, but it's not always the case. So keep that in mind, it's not always the case. Let's look at this example here. When there's 3 different groups, so I have a CH3, Br, and a H. This can show cis trans because look at the left side, they are different, and look at the right side, they are different. So it's fits the criteria, they will show Cis Trans Isomerism. And to determine Cis Trans, it's easy. We just look at if the same group is on the same side, that's the cis. And if it's the opposite or diagonal side, that's the trans. Okay, but for E and Z, it's the priority that we need to look at. Okay, let's go this way. This goes to a 1. This goes to carbon, that's a 6. So this is at priority. Going this way, it's a 6. And BR, let's go to the periodic table. BR is a 35. That's definitely higher in priority. So this is opposite side. So this is E. So this time, cis is not a Z. Do you see that? And therefore, this 6 and 1 priority, 35 and 6 priority. This is the same side, so it's a Z. Now trans is a Z. So you see, it's not always that Z is a cis. Now, if we've got all 4 different groups, we're just going to use the E and Z system. So H, we know it's 1. Cl, what was it just now? 17. Okay, so that's that priority. And this is a 6 because it's a carbon, and Br was 35 just now. So priority. So this is an E. And yeah, 17 and 1 priority. 35 and 6 priority, same side, so Z. The cis trans or EZ isomers, they've got similar chemical properties, but it's possible that it's different as well. They react with the same reagent, but with different rate of reaction. And they would have different physical properties like melting and boiling point. I'm going to draw the cis and trans, one of the more simple ones, like 1,2-dichloroethene here, to demonstrate the melting and boiling point. Let me draw that first. So I try to arrange the cis and trans in solid state to demonstrate its melting point. So I put them close together like this so that I can compare the cis and the trans. Okay, so we know that Cl is slightly more negative, delta negative, compared to the hydrogen, delta positive. So in this way, they've got permanent dipoles, but this way they've only got London forces. London forces, permanent dipole, permanent dipole, permanent dipole, London forces. Okay, we know that London forces are weaker, permanent dipoles are stronger. So going this way, I can see permanent dipoles, but going this way, I just see London forces. What about the trans? So if I have this delta negative and delta positive and delta negative, this way it's permanent dipoles, and this way as well. Permanent dipoles, permanent, permanent, permanent. So there's more permanent dipole in the trans that makes its melting point higher. So they've got different melting points, which means cis and trans have different physical properties. Now I'm going to compare its boiling point. For boiling point, they're in liquid form, so I'm not going to draw like this in this nicely arranged manner. I'm just going to mess it up a little bit. Now, under chemical bonding, you learn about dipole moments, whether a molecule will have a dipole moment or not. If the pool of electron cancels out each other, then they've got no dipole moment. So looking at the cis and the trans, the cis has a permanent dipole here, a dipole moment here, because chlorine would love the electrons much more than hydrogen, so it's pulled towards that side, making this molecule delta negative on this side and delta positive on this side. And permanently, again, the chloros are here, delta negative here, and delta positive here. This is a permanent dipole. Now looking at the trans, it's pulled this side and this side. Don't they cancel out? It's the opposite direction. So this delta negative actually cancels out each other. So it's almost not there. It got canceled out. So I'm going to say this is just London forces, whereas this is a permanent dipole. So we know that permanent dipoles are stronger, which means the cis is going to have a higher boiling point. So this drawing explains why trans have higher melting point and a cis has higher boiling point.